All right, welcome back, everyone. Today we're going to look at independent and dependent events and probabilities dealing with those types of events. All right, now we need to understand what these two things are. We talked a few videos ago about what an event is, and it's just an example of something that can happen. Now, a compound event is when two or more simple events occur. Okay, so just think, you take a coin, you flip it a couple times. Okay, as long as it's happening more than once, so two or more times, it's considered a compound event. Okay, now with compound events, these things can happen one of two ways, as either independent or as dependent events. Okay, so independent and dependent, these are two pretty important ideas. Now, independent events are based on when the outcome of the initial event does not affect the next event. Dependent events occur when the outcome of the initial event does affect the next event. And the basic example I can give you is if you are put into a raffle for a drawing of some sort, and there's 12 tickets in there, and they draw a ticket out, and they leave it out and draw a second ticket. When you draw that second ticket, there are only 11 tickets left. So that first one had an effect on it. Okay, so that second drawing was dependent. Now, if they drew that ticket and put it back in there, there's still 12 total tickets in there. And so, since the sample space didn't change, that is an independent event because you're still dealing with the same number that you started with. So one of the things we want to be able to do is determine if it's dependent or independent. Okay, so here's the first. One coin is tossed, and then a second coin is tossed. Now think about this logically. If you toss a coin, you've got a 50-50 chance of hitting heads or tails. Okay, 1 out of 2. If you pick that coin up and flip it again, does that probability change? And the answer is no, it's still 50-50. So because it's still the exact same, those two things are considered independent. Okay, now the second one. In a raffle, a ticket is pulled, set aside, and the second ticket is pulled. Now I kind of alluded to this already. But when you draw that first ticket out, you have one less to choose from, so your probability actually improves with that second pull. So the second pull is influenced by the first one, so we say that that is dependent. Okay, so that's kind of the idea behind this. So just read through this one. I'm going to pause for just a second and see what you think. So a card is selected from a deck and replaced. Then a second card is pulled. It is not replaced. A third card is pulled. What do you guys think? All right, now let's take this two at a time. So a card is selected from a deck and then it's replaced. Then a second card is pulled. Well, when that second card is pulled, that's independent because you still have the total number of cards there. But when you take that second card out and it's not replaced, and then you draw that third card, that is dependent upon that second pull, so this one is a dependent. Okay, so this one actually has both depending on how far you take the problem. All right, so hopefully that idea makes some sense. Here's when we need to use this. So when we want to know the probability of multiple events, we multiply these things together. Okay, and the key word here is this and. So probability of A and B. So what you do is you find the probability of each by themselves. So we find the probability of A, we find the probability of B, and then we multiply those together. Okay, so the example that they're going to go through, and we're going to see what you guys think, is you have a bag of marbles with 7 red marbles and 5 blue marbles. You draw a marble, you replace it, and then you draw a second marble. Okay, and then so on. We want to find the following. So we want to know what's the probability of pulling a red, then a blue, then a red. So we're pulling 3 marbles total. Well, start with the first one. What's the probability of a red? Well, you got 7 marbles that are red. You've got 12 total, so that's 7/12. All right, now remember, you put that marble back. You then draw a blue marble. That's going to end up being 5 out of those 12. All right, so far so good. Then we put that marble back, and we pull another one. Well, we're back to reds, and there's 7 again, so it's 7 out of 12, and you get that. Now, you take these things, and you multiply them together. Well, 7 times 7 times 5 is 245. 12 cubed is 1,728. Those don't reduce down. Okay? And there's your final answer. That's your probability. Okay, let's look at this next one. Go ahead and pause the video and give this one a try. Okay, so for this one, we take blue, blue, red. Well, blue was, remember, 5 out of 12. We put it back. We got blue again, so that's 5 out of 12. We put it back. Now we're going red. That's 7 out of 12. And then you just multiply. So 5 times 5 times 7 is 175. Our denominator is still 1728. And there's your final answers. Okay, so when you're not replacing something, you keep those total sample space, that number of outcomes that are possible, the same. All right, now here's where it changes. What if we set a marble aside? Okay, so we start with this. Find the probability of a red, blue, red. Well, for the first red, it's still 7 out of 12. Now, for a blue, well, there's still 5 blues in there, but we no longer have 12 marbles. We have 11 marbles. Right? And so we have to make sure that denominator reflects that. Then, for the last one, we're looking for another red. Well, remember, you took a red out already. That was the first thing you did. So you no longer have 7 reds. You only have 6 in there. And that means that we have 10 marbles total. So it's 7 times 5 times 6. Okay, now you multiply those together. You get 210 over 1320. Okay, we can take that and reduce. Once you reduce, let's see, 30 is going to go into each of those. So you've got 7 in the numerator, 44 in the denominator, and there's your final probability. All right, so using this same idea, try this one here. Probability of blue, blue, red. Go ahead and pause the video. Give that a try. Okay, so you guys should have had that chance to do that. So let's look and see what you got. So for a blue, we've got 5 out of the 12 that we have in there to start. Then we pull another blue. Well, remember, there's no more 5 marbles. We're now down to 4 and 11. And then we go to a red. There's still 7 reds, but there's only 10 total marbles in there. Okay? And so you end up with this. Now, simplifying that down, when you multiply, you get 140 over 1320. Okay, divide this out. 20 goes into each of those, and you end up with 7 over 66, and there's your final probability. All right, so there's a basic start to independent and dependent events. All right, let's keep going. So next one deals with decks of cards. So 3 cards are drawn from a deck of cards. If no cards are returned, excuse me, if no cards are returned to the deck, find the probability that all 3 cards will be diamonds. All right, so let's think about how to do this. 3 cards are drawn from the deck. What's the probability the first card is a diamond? Well, if you think about a deck of cards, there are 13 diamonds out of 52 cards in the deck. So we got 13 over 52. Now, if I don't put that card back in there, my denominator can't be 52 anymore. It's now 51. Okay? But I'm also pulling a second diamond. So there's not 13 diamonds. I'm down to 12. Okay? Then you pull a third card. Well, there's no 13 diamonds. There's no 12 diamonds. We're down to now 11 because we've already taken 2 out, and we are left with 50 cards in the deck. So there is your setup for this type of problem. And now you just multiply out. So 13 times 11 times 13 times 12 times 11 is 1,716. 52 times 51 times 50 is 132,600. And now to finish this up, we divide it out, simplify the best we can, and when you simplify, this simplifies down to 11 over 850, and there you go. So if you were to go and draw just 3 random cards, 11 out of every 850 times you do that, you should get 3 diamonds. All right. Final one for today is this. What is the probability of rolling the numbers 1 through 6 in any order on a dice that you roll 6 times? Now this one's really tricky. You got to think about this. Start with the first one. You roll a dice. What's the probability you get a number 1 through 6 on that first dice? Well, if you're really thinking about it, you're guaranteed to get a number 1 through 6. So there's 6 things you could choose from out of 6 total possibilities on the dice. So it's 6 over 6, or 1. You're guaranteed to get a number. Now, in the second roll, I need a different number. I can't get the same number I got the first time. So how many could you get? Well, you can get 5 numbers. Okay, but there's still 6 to choose from, so it's 5/6. Now the third one, I've got 4 numbers left because I've already had 2 that I've rolled, but I've still got 6 possible numbers that I could do. Okay, then continuing on with this same logic, you've got 3 for the next one out of the 6. Next one would be 2 out of the 6th, and then finally, if you did this correctly, you would get 1 out of those 6 dice, 6 possibilities on that dice. And so we multiply this together. So your numerator is 720. Your denominator is 46,656. And then we simplify this down. And when you do that, oops, I got the wrong thing here, so give me 1 second. When you simplify this down all the way, you end up with 5 out of 324, and there's your final answer. So basically what this says is if you roll the dice 324 times through this 6 roll cycle, 5 of those times you should get the numbers 1 through 6. Alright, there is probabilities of independent and dependent events. Hopefully you can kind of see the difference and understand how they work. If you have any questions, definitely contact me, and I look forward to helping you out. Good luck.